Measuring reionization with IGM damping wings towards quasars. We heard about IGM damping wings towards galaxies, but we didn't hear about quasars yet. All right, so here are all the constraints on reionization that we have so far in the literature, right? And I'm like, why do we even have a reionization session at this meeting? Like, it's solved, right? Like, just average all these data points. And like, you know, we've measured the reionization history to like super high statistical precision, and like we can all go home, right? But remember, so no one's written that paper yet where you combine all these measurements, right? And remember that the reionization history is a cosmological parameter, as was mentioned by Martin, and it's degenerate with things that, you know, lots of cosmologists spend lots of time caring about, like, you know, the Hubble constant or sigma 8 or the mass of massive neutrinos, right? And so, you know, the people that do things carefully, that's what they use, okay? They use those constraints, right? So the issue is really like, nobody believes any of this, right? I mean, it's, you can put a point on a plot, but nobody actually believes any of these constraints. And so we need to figure out how to work harder such that cosmologists and others will actually believe what we're doing when we say we're constraining reionization, okay? And so the technique I'm going to talk about is IGM damping wings. It's pretty simple, okay? There's foreground neutral material. Okay, it imprints a damping wing on a spectrum of an object, and basically all constraints on reionization besides these two model-independent ones essentially rely on this technique, okay, with the exception of 21 centimeter, which someday may work, but hasn't worked yet. Okay, so the way that it looks with a quasar is that it's a little more complicated because we have this nuisance process, which is the radiation from the quasar itself. That was the quasar lifetime that Christina was invoking, right? And then the foreground neutral IGM imprints this damping wing signature on the quasar. And so then the issue is like, well, we don't know this intrinsic spectrum of either a quasar or a galaxy, actually, right? So we have to solve for several nuisance processes, the continuum, the lifetime, and also what the IGM is doing. Okay, and the nice thing about quasars is that we have hundreds of thousands of low redshift quasar spectra that we can use to train this model, and that the physics here, right, of the proximity zone is actually sort of ab initio, first principles kind of thing. We can just simulate 1D radiative transfer pretty easily. So I claim that the quasar technique has the advantage that it's very clean. Okay, and so but it's not super easy, right? And so you have to think about what you're doing, right? And so you have to be careful here. So we have to infer all these things. We have this nuisance stochastic process, which is the quasar continuum, right? And we essentially model it with a dimensionality reduction model. There's that dimensionality reduction is never perfect, so then there's a correlated random process, which is the residuals, and then the IGM is itself a stochastic process that we also have to model, right? And so what we're doing then on the quasar spectrum, the fancy word for this is that we're doing field level cosmological inference, right? So we're basically modeling all the pixels in order to get out the model, okay, or in order to get the model parameters that we care about. Okay, so what does this look like? Well, we've run, you know, thousands of mocks to be sure that we're actually recovering the true cosmological parameters. So imagine the possibilities if you could actually believe your error bars. So we've tested that, right? And so here's a mock quasar spectrum. The truth is 0.25. Neutral fraction, the lifetime is 10 to the 7 years. And you can see that we're reconstructing the continuum very well. And we're also getting out the model parameters. We marginalize out the nuisance process, which is the quasar continuum. And then we're left with these constraints on the lifetime and the neutral fraction. Okay, and again, that was a mock data, okay? But JWST is getting all these beautiful spectra, okay? And there's also the XQR30 data, so there's plenty of spectra from the ground. And so now we can apply this method, now that we know we believe the error bars, in bulk to all of these wonderful spectra that we have. And so here's an example of a JWST. Well, so these are two spectra from JWST. I'm going to focus on this one here, right at redshift 6.8. And so there is the spectral fit, okay? You can see that we're reconstructing the continuum very well, and also the transmission profile. And what is the answer? Well, unfortunately, I'm out of time. You know, it's not really something I can fit into a 5-minute talk. So yeah, please pay. If you subscribe, you can view the premium content past the paywall. Thank you very much.